Hello and good evening to this latest edition of ESR Connect. My name is Helmut Prosch. I'm a radiologist from the Medical University of Vienna, focusing on thoracic radiology. And I will host this episode today, focusing on AI and how AI can help to battle COVID-19. We have a very distinguished panel of speakers today, Alberich-Bayarri from Valencia and Georg Langs from Vienna. And I would like to ask both of them to introduce themselves. Georg, would you, first off, Angel, would you start to introduce yourself?
Yes, thank you for the presentation. So my name is Angel Alberich. I am a biomedical engineer from Valencia, and I am the founder and CEO of QUIBIM. And mainly we are working in image processing and artificial intelligence also in these COVID times.
Yeah.
Yes, hi, my name is Georg Langs. Very much thank you for the invitation. I'm here also in Vienna. I'm part of the Medical University Vienna, where we are running the computational imaging research lab as part of the Department of Biomedical Imaging and Image-Guided Therapy. And I'm also here as one of the co-founders of ContextFlow, which is a spin-off of our university and creating machine learning software for image analysis.
Thank you very much. As some of you may already know, ESR Connect is meant to be a very interactive session. So I will invite all of you to ask your questions online, and we will try to answer most of them as much as we can. I would kindly ask you to focus your questions today on the topic at hand, so AI, and how can we implement AI applications, or how can we develop AI applications. To start off this session, I would like to give you a brief introduction into the topic, and then we will move on with the more technical issues. Could you change to my slides, please? Just a second. Okay, thank you very much. I was asked to give you a brief introduction into imaging in COVID-19 and how can AI help. So, as you may know, imaging plays an important role in COVID-19, in the battle against COVID-19. And this doesn't work. Can't move my slides. Okay. And okay, so the first slide is lost. So in general, we have two modalities we can use in COVID-19, chest radiographs and CT. And in both cases, you should think about the use of these modalities very carefully. We use both imaging modalities to confirm the clinical suspicion in patients with negative PCR. So if a patient comes in with a high suspicion for COVID-19, but PCR is negative, we perform imaging. Usually it's CT in our center at least. And then we also perform imaging in order to propose differential diagnosis in cases in which the diagnosis of COVID-19 is not established, or to diagnose comorbidities. And furthermore, we use imaging to diagnose complications, and also we use imaging for risk stratification. Importantly, use imaging very sparingly, because this is associated with a certain risk for the personnel, and also our patients waiting outside the ward. Okay, so what are the indications for chest radiographs in COVID-19? Chest radiographs are in most centers the primary imaging modality. However, chest radiographs should not be used as a screening test or in patients with only mild symptoms. However, it is indicated for the initial assessment in patients with COVID-19 with moderate to severe symptoms, in particular in resource-constrained environments. In other settings, you might use CT. And chest radiographs are also used to follow patients, but also again here used sparingly in order to avoid an infection of your technicians. What about CT? Indications for CT are also pretty much the same like in chest radiographs. You should not use it as a screening tool. However, it is indicated in patients with moderate to severe symptoms in order to risk stratify these patients. And then CT is also primarily indicated to exclude additional complications such as pulmonary embolism, something we will tackle in one of the next episodes, pulmonary edema or bacterial superinfections. So what we do when we read our radiographs or CT scans, we try to come up with a diagnosis in times like we are living in right now. The question is quite often, is this COVID-19? And if we are asked such a question, we should answer it by giving a suspicion level of the CT diagnosis or chest radiograph diagnosis. So the probability in some cases is very high, in cases with very typical findings. And in other cases, we can exclude any visible pathology, maybe the imaging was done too early, or we can suggest alternative diagnosis. And then there are cases in which we are not that sure, we call it indeterminate for COVID-19. And in these cases, we should advise our clinicians that this could be COVID-19, they should isolate the patient, and the patient should be investigated further to include or exclude COVID-19. So what about typical findings in patients with COVID-19? The typical findings, in particular on CT, are summarized as follows. We see in these patients frequently ground glass opacities. Ground glass opacities are the earliest signs of COVID-19 with or without consolidations. As the disease progresses, we see more and more consolidations. And in the further course, we see then also these arcade-like lines and linear consolidations, which resemble and are organizing pneumonia. In the early phase, we also see quite frequently septal lines or crazy paving, and we see these findings in the geographic distribution. And strikingly, sometimes we see these ground glass opacities with a round morphology, which is something we don't see in many other pathologies, or we see the atoll sign again pointing towards organizing pneumonia. Interestingly and importantly, in many patients, but not all of the patients, we see a clear basal and subpleural predominance of these findings. And these findings are usually multi-lobar. What about findings which do not point towards COVID-19, point towards another direction? And if you see findings like a tree in butt abnormalities or perihilar ground glass opacities, this points towards other pathologies. The same holds true for pleural effusions, lymphadenopathies, cavities, and solid micronodules. Be aware that in advanced stages, you may see pleural effusion, in particular if the patient develop heart failure. And in these cases, and also in superinfections, you may then also see lymphadenopathy in patients with COVID-19, but this is primarily pointing towards a complication of the disease. What about the more challenging issue, the indeterminate for COVID-19 situation? And in these cases, you're not sure that you're dealing with COVID-19 in a context in which you would not be in a pandemic situation. You would not even think about COVID-19. But this is a patient like here, a patient with known lung cancer here on both sides, a multifocal lung cancer. And in addition to that, in the follow-up CT scan of this patient, we found in the upper lung regions, we found these rounded ground glass opacities on the left side. So you're not sure if this is COVID-19. It could be COVID-19. It could be associated to another viral infection primarily, or it could be drug related. So that's a case where you should state that this could be COVID-19, but the probability of COVID-19 is not as high as in the cases I showed you before. In this case, COVID-19 could be proven by RT-PCR. So where do we get help, and where do we expect help? And this is another thing we need to do. We need to look at the extent of the disease in order to give the clinicians an impression on the risk for developing complications. And there are a number of proposals on how to judge on the extent of the disease. Essentially, that's done by most of us by a visual inspection and visual impression. So how can AI and computers help us in these situations? And a variety of situations in which AI could help us. Starting off with, it could help us to increase the confidence of the diagnosis in cases with indeterminate imaging. And this becomes more and more important as we are now moving into a period of time in which we don't see as many cases of COVID-19 as we've seen before. So in these situations, the identification and quantitative diagnosis of COVID-19 becomes more and more challenging. And these are the situations in which I would love to get help from AI algorithms. And furthermore, our clinicians in particular would also like to get some more clues, some more help to predict the course and severity of cases, to predict complications and to diagnose complications, and to predict the outcome of patients. So that's for the introduction. And without further ado, I would like to ask Angel to start with his first technical presentation.
Thank you. So perfect. I hope you can see my slides. Well, it's a pleasure to present to you, and I will discuss mainly on the timeline in developing algorithms, mainly on the working steps and how pandemia is affecting this normal workflow for AI algorithms development. Okay. So basically, we identify internally a timeline or a stepwise development of the algorithms. This is the philosophy we follow both in my research group and in the spin-off company. So as you can see in the left side of the slide, we have this kind of a stepwise approach for the development of quantitative imaging algorithms. And let's consider here that we are considering AI as a kind of quantitative science by which we extract, let's say, deep features from the images, and we use the convolutional neural networks to perform classifications. No? One of the keys for the timeline for the stepwise process of the development of the algorithms is to always start by a kind of proof of concept, which defines the clinical idea. And then we will go to work out the proof of mechanism, how to acquire the images, how to process them. And basically, this is a process that has been traditionally used for the deterministic algorithms, so-called also algorithms to extract imaging biomarkers in our domain. But you can see in the right side of the slide what would be a summary of a traditional process to perform an AI model. One of the most relevant learnings that I think we have in our environment is that AI should be driven by the clinical need and not the data set. Sometimes we find data sets and we understand that it is a bad practice to take that data set and try to create the clinical problem from the data set. So imagine that we find 7 million CT scans. We will try to solve all the problems of CT scan with these 7 million. No? We prefer to start first by defining the clinical need to meet the clinicians to understand where there are unmet solutions. So then we go to the next step, which is the data set design. And we understand that the data set design is a highly relevant step in AI, and it has to be after the clinical need and not before the clinical need. Then once we have this data set already designed, we will additional processes of AI, and finally generate a way of displaying our results and the information, how we will report the outcomes of the AI model or the algorithm to the user, to the clinician in the end. So here you can see the timeline for, let's say, developing algorithms for research. And you can see that to develop a new algorithm, it can take more or less in AI from 1 to 6 months. We have to go through the steps of data preparation, the design and selection of the architecture and the model training, testing, and validation, the hyperparameter scanning, and finally the release to production. From these steps, all data scientists will agree that one of the most demanding ones is the time to prepare the data set and to do the data set preprocessing, to curate the quality of the data we have and to organize it. Once you have that, the rest is more straightforward. But I would remind that these are the timeline mainly for a research algorithm. If we are thinking on bringing a research algorithm to a product, to a real product, then we have to think on the timeline for certification. And you can see that for certification, we will discuss on the specification of the intended use. We have to be very specific on why the algorithm is, on what is the algorithm going to be used for. Also on the data set justification, we will need to collect data from different centers, different image characteristics, different countries, controlling all sources of variability. Regulatory agencies are very strict and more strict with AI algorithms in terms of collecting information from different sites in the data sets we use. Then we will have to write a device description, to write a user manual, to perform a risk assessment, more let's say, regulatory steps, and finally, we can get a certified algorithm, and this will not happen before 6 or 18 months. So we can see that globally, the timeline for development of a new algorithm and bring it, let's say, to real clinical application can go from half a year to 1.5 years, more or less. So this is an example of one of these algorithms. In this lecture, I will focus mainly on the chest X-rays classification. From COVID, we have been working in CT as well. In chest X-rays, we developed an AI algorithm, and this is an example of how an AI algorithm can be developed with a multi-labeling neural network. This is taking a chest X-rays. Basically, this neural network is structured in an architecture called DenseNet 121. It's an architecture that allows to extract all the deep information of the image and taking a lot of sensitivity to the different degrees of detail of the image, thanks to this more, let's say, complex architecture. We decided to create a work in curation, and we took the most relevant data sets available worldwide, also own data sets, and we designed a common data set of 500,000 images. We decided to group those data sets in 5 different families, diseases or alterations related to the lung parenchyma, pleura, mediastinum, and bone, and also heart. And we decided to include those classifications inside, so we involved 15 pathologies. And then this is an example of how an optimized classifier can provide the information on the abnormal probability in the end. This is an example of how AI can be communicated, and in this kind of report, we can summarize the main outcomes of an AI algorithm, and here we can see the heat map information. That's showing the regions of the image that influenced more on the classification. Also a list of the most probable findings, and In this case, we have to always analyze what is the threshold for the increased area under the curve and the performance. In this case, we identified that an abnormal probability score of 0.3 was our threshold to better differentiate between a normal and abnormal. This information in an intuitive way, then radiologists can get a support, an objective support with a score like this abnormal probability score in daily practice, no? And we recognize that many radiologists now in the COVID-19 stage have suffered from stress to have to report many different chest X-rays in a single day, and they were recognizing that if they had kind of objective quantitative number to measure the degree of abnormality of the chest X-rays, this could have been very useful to avoid biases in the interpretation of the images. And to end my kind of first presentation on this part, I would like to finalize on how we have adapted the timelines in this pandemia stage right now. So pandemia basically is introducing changes in the algorithms timelines. So if we think on how to adapt to this quickly changing situation from February, basically working completely normally, and suddenly lockdown in March. So we have to react. In COVID-19 pandemic, we have to be as fast as possible, being useful to the healthcare system. I like very much one video you can find in YouTube from Michael Ryan from the WHO. There were several very important sentences in this video for addressing a pandemic situation. And these were some of my favorite ones, no? That you need to react quickly, you need to go after the virus, you need to be fast, you need to be the first mover, and if you need to be right before you move, you will never win. So basically what we did is, instead of waiting to deploy a new COVID-19 algorithm that can be more time consuming, we analyzed if our current algorithm was sensitive to COVID-19 findings in chest X-rays. We detected that the classifiers usually activated were mainly the consolidation, mass, atelectasis, infiltration, edema, pleural thickening, and of course the abnormality score as well. So it's important to know that we have not been COVID-19 specific, but from the degree of abnormality, in the end, we are able to measure if a chest X-ray is abnormal and to provide the support to the radiologist. So what was the first move? The first move was to install chest X-rays classifier, even if it's not COVID-19 specific, but at least sensitive and CE marked. And what is the work in progress, no? The second move happening as we are speaking, to create a specific version for COVID-19 through international collaboration, no? And on those projects we will discuss afterwards mainly. And thank you very much.
Thank you. Thank you, Angel. There are already two quick questions. One is, what kind of data pre-processing did you use?
Well, in these data sets, we do data augmentation and we do normalization mainly as a standard. And then we verify also all the different classes in the data set to harmonize the different characteristics. So if you take, for example, chest neck 14, it has labels that are completely different to other data sets that you can find publicly, no? Like, for example, PACHEST or any other data set that's available. So what we first did was a harmonization between the different data sets in, let's say, 5 different families. Then inside those families, we create also groups for the different, let's say, keywords or findings until we had 15 different classifiers. And for each one, we created data augmentation for each, the training of each classifier. No? Data augmentation was mainly consisting on rotations. And then we had the normalization also of the images, and obviously the image resizing, no? and that was the pre-processing.
Thank you very much. The next question is on the ethics approval and collaboration, and I suggest that we will answer that together then after Georg's talk, because Georg will also address some of these questions already. So Georg, would you continue please with your presentation? I'm afraid we have some technical issues with the presentation of Georg. Okay, until we solve them, Angel, could you just... It's okay, perfect.
Okay, sorry for the technical difficulty. So I hope my slides can be, yes. So Angel gave you a detailed insight in how to develop an algorithm to tackle problems that we need to solve in the context of COVID. In the next couple of minutes, I'd like to give you an overview of the types of approaches that came up, that were developed in this very brief period of time during the initial phase of this pandemic. And I think what's striking about the role of AI that Helmut mentioned at the beginning of the show was that this is actually pretty volatile. So in the beginning, when we had a high volume of CTs and low-dose CT was actually used for screening, the real job of AI was to take the load off the limited resources to assess these CTs and give a very rapid assessment whether this screening CT, low-dose CT, shows signs of COVID-19 or not. I think that is changing. We also see it in the guidelines. And so the now emerging role of CT and of artificial intelligence and machine learning in helping us to use CT is deciding whether it's COVID-19 or not in the more tricky cases. I think there is still some relevance, of course, because the testing is quite relevant false negative rate. So there is a role still in deciding whether a patient has COVID-19 or not for AI in CT. And I think this role is also shifting in not just doing the classification, but providing the clinicians, the radiologists with additional information. So with suggestions, with scores, and with the content you need in order to make this decision. And I think the last part that's particularly interesting because that's emerging right now as we are moving into a phase where we have to manage the patient volume, to manage the individual patient, to also start to really go for the optimal treatment, is that based on the CT data and also based on other data that is available for these patients, we have to predict something about the severity of the disease, the care need. Will this be a patient who will need ICU or mechanical ventilation? Is this a patient whom I can send home? So I think this will be a big job of artificial intelligence and machine learning models in creating these predictions and providing certainty of these predictions from CT data and connected information. So I think what's striking here is that the role of AI was not fixed and clear from the beginning, but it actually expanded and shifted over the time of the pandemic. And I think that will continue to be the case. But I think these three roles are the main ones. And I think they are also a bit heterogeneous across different geographic areas, which is, I think, also one of the features of AI in medicine. The three types of approaches that we've seen are approaches that work directly on the imaging data. I think Angel mentioned a couple of them. So using something like a CNN, a convolutional neural network, to directly from the imaging data get the estimation, the prediction, this is a COVID-19 or not patient, or any other thing that you would like to predict. The core here is that you are working directly on the imaging data and have some kind of end-to-end architecture. The second approach, and I think it's a slightly more strategy that makes use of the data and of our knowledge better, is, and I think Angel also mentioned some of these ideas, that we can actually divide this prediction step into two parts. One part is deriving the presence and the distributions of known patterns from the imaging data. And then on top of that work, to do prediction, to do diagnosis, to do classification or any other support based on these identified patterns. That has two advantages. First of all, for this initial step, developing ground glass opacity or reticulation or consolidation detectors, we don't need just COVID patients. We can do that. We can learn that also from other patients. There are a lot more data available in the initial phase of the pandemic, so these become more robust models. And then on the second part, on the prediction part, we know a lot more about the mechanics, about the distributions, and about the connections that we would actually like to model. So in the second part, this is an approach where you can deal with a comparably low number of actual COVID cases and non-COVID cases for your training, and can draw on a large population of existing infectious diseases of the respiratory system to train your initial phases of the model. This is also something where a lot of discussion was done over a long period of time in terms of transfer learning. I think that's a very clear hands-on example of transfer learning. Learn something from a large population and then do the last bit, the classification of the population that you have on the particular disease. And I think one approach, and that's the third one that becomes more relevant now when we are moving into prediction, is that we not only want to use imaging data, but also other clinical information that we have about the patient. Because clearly it turns out that a lot of this clinical information has a lot of very solid predictive power for the severity of the disease, for the future course of the disease. And so I think connecting what we can draw out of imaging data and these parameters is key. And I think this is where many groups are working on right now. I think an interesting aspect, and I think that's very relevant to have in your mind, is that during this initial very hectic phase of trying to develop something that works, something that helps us to deal with the number of patients, with the need for very quick decisions, with limited resources, especially during the initial phase where the testing was not widespread, is that methods popped up, and a lot of that popped up in preprint servers. So methods were shared, results were shared that did not go through review. I think that is in itself actually not a negative thing. I think it's a positive thing because it adds to the speed with which ideas can be exchanged, and in which mistakes don't have to be done a couple of times. But I think it very importantly puts a lot of responsibility onto the reader. So we have to read these papers with things in mind, like the integrity of the data, the reporting, and the transparency of the data these models were validated on. I think there's a very good paper by Weinand and colleagues that came out that reviewed many of these initial works, and I think there are still a lot of works coming out. And I think the two main important points are you have to be aware of the balance of the data set. So among the initial results, there were many results where the non-COVID cases were from one set of institutions and the COVID cases were from a different set of institutions. And that meant that a lot of the classification results, it was not clear whether this classification was actually picking up on signs of COVID disease or whether they were just becoming very good at differentiating between different acquisition parameters. What I found positive is that many of these papers were very transparent in reporting this. So it was clear once you read the results section if this is a balanced data set or not, and you could judge the results accordingly. A big red flag is, I think, happening in papers where this is not reported transparently, because if there is no transparency on the composition of the cases, the positive and the negative cases, from which different institutions they are coming from, and the balance of this drawing of the data, where this is not reported, it's really completely unclear what you can conclude from the results of this study. So I think an important takeaway point is look at the composition of the validation test set. Are there confounds that correlate with COVID versus non-COVID, or other values, like, for example, the severity of the disease, the need for ICU, the need for mechanical ventilation? I think we will see this popping up in the future. That will be important to understand, is this a balanced data set on different institutions? Because we, of course, know that the use of ICU and the use of mechanical ventilation is not only a function of the indication, but also a function of available resources. And so I think the key takeaway for me was that transparency is really important, and early sharing of results and data is important as well. And I'd like to conclude with one very recent example study where I think all of these points were done right. And this is done by a group in France, by Casagnon and his colleagues, together with Nikos Paragios. And they looked at data across 6 institutions. They trained their models on one set of institutions and then applied the model on a different set of institutions in order to validate the accuracy. They compared their model not only with a single reader, but with multiple readers. So we also know the certainty of the annotations that these models are compared with. In the second step, I put this figure in the middle. They not only performed the black box prediction of the severity of the disease for individual patients, but actually took care in being transparent about which features do contribute to this prediction, which features are actually correlated, and we already see that some of them actually conform with the expectations we have, and some of them seem to be signatures or biomarkers that might be novel and that might be helpful in the further kind of improving our prediction accuracy. With this brief overview, I'd like to hand over back to Helmut and Archel.
Yeah, Georg, thank you very much. As an information for all of you interested in doing research in this topic but struggling with the data sets, on the EBA website, the link is listed below here. You will find a wealth of information, not just information, but also data sets you can use for your research. And it is worthwhile to go to this valuable website to get more information in case you are interested in doing research there. Okay, so we got a number of questions for both of you, and I'd like to start off with Georg. And what you mentioned already, and also Ankel did, speed is of the essence. And when we look at the Chinese studies, and some of which are really good, they used a population from China, which might not be representative for a European environment. And in particular, it might not be representative in phases in which we don't see as many cases of COVID-19 as we saw weeks ago. So might this impair the quality of the software we then use, and might this have led to overfitting?
So if I may start, I think that's true, to be very aware of this danger of overfitting and of the sensitivity of many of those approaches to particular imaging parameters. And so I think what you have to do is you have to look for diversity in your training set. So if you train just on one population and one set of imaging parameters that might be prevalent in a screening scenario, then the model will not work well in data that is acquired in more high resolution settings. So I think you have to take care that both in the training and in the validation, all of this data is represented. And I think that's true for all AI approaches, but I think it's particularly important here, where, of course, we see a shift from available data that is shared, and I think it's a very positive sign that a lot of this data is shared across the community. But I think overfitting is a problem, and the solution for overfitting is to draw training data and validation data across many institutions, and especially across institutions where you actually want to apply the AI algorithm.
And to adapt it according to the prevalence of the disease.
Yes, I think that's a second point, and that's a bit more subtle point, but of course, some of these models might be susceptible to the prior distribution of the cases that you use for training. And so as this shifts, as this changes, as the parameters with which you acquire the data start to correlate to some extent with the severity of the disease, when you don't use it for screening or for unclear cases, but really for severe cases where the primary need is in prediction of the course of the disease, this has to be taken into account. Yeah.
Ankel, do you want to add something to that?
Well, I agree completely with Georg on what he was mentioning. I think that working from a data set within a specific group of population and then trying to generalize that algorithm is more complex than if you develop an algorithm with the wider group of population possible. And therefore, for that, all the international consortiums and the repositories and the projects that we are very much used to build in Europe are more rich in terms of variability in the data set. So we already have experience on developing algorithms in, for example, in Europe, and taking for those algorithms data from US, data from China. And then thanks to this rich variety of data, you can perfectly take an algorithm to Taiwan and it is working. One of the papers I was showing in the previous presentation was from validation of our algorithm in a Taiwanese data set. Our algorithms were not trained previously in Taiwan, but they were good enough to generalize in that case. So I think, yes, as we were discussing, as richer the data set can be, the better.
Thank you. And there are two questions regarding a topic we all are struggling with, which is the ethics committees. Nowadays, it's getting easier to get the approval for ethics committees as the ethics committees try to be very fast in COVID times. But your product goes back to a time where it was not that easy. So how did you get the approvals from all the centers, from all the ethics committees, and did you ensure cooperation? And furthermore, do you think that this speedy process should be kept like that, or should we then step back and take it more slowly as soon as the pandemic is not the big issue anymore? Angel.
Yeah. Well, I think that the fact of being fast from the ethics committee perspective means that they are meeting more frequently, but the data they are requesting is the same. So they are requesting research projects, they are requesting all the agreements, and therefore their inputs are the same, the outputs are the same. What is changing is the frequency that they are evaluating their proposals, to my view, to my impression. So obviously it's a better perspective for research that we can get this kind of fast track approval. And it's true that we have to undergo this way. There has been wide discussion on whether GDPR being so strict in Europe has been hindering research, for example, in pandemic situations. But as of now, I think that for our experience, we are running a project with different hospitals, and we could never imagine to get such a high amount of ethics committee approvals in such a short period of time. So we agree that because we think that we are in an exceptional era right now.
Yeah, thank you very much. For the interest of time, I'd like to continue, Angel, with your presentation. And then we move on to Georg's presentation, and I hope we will then have enough time for more discussion.
Okay, thank you. So previously we discussed on the timeline for AI algorithms, and now I wanted to introduce more or less the projects that we are involved in. February 14, we already published in our blog our concern on the COVID-19 and how we could help, mainly because we had been detecting that in Taiwan, in Italy, some places where we did have connections, we already saw that obviously imaging was becoming more and more crowded in terms of emergency patients for COVID-19. And if you remember also, February 14 was the first death in Europe, in European territory. So we become rapidly sensitized, and we decided to publish this blog on an idea that we already had in our group and that we are working with it right now, which is let's try to first use the classification of the chest X-rays images, and we already saw the chest X-rays classifier, but in the end, this is in a patient level. This is not in a population level, and we are in a pandemic moment. And if we are in a pandemic moment, we have to see the problem both at a single patient level from AI, but also as a population level analysis. And that's why we decided to implement a pipeline by which we can automatically segment the lungs and in the chest X-rays. And from those lungs, we can extract many radiomics or textural features, because in the end, textures we think that might describe the different patterns of the pneumonia damage in the lung parenchyma. So we decided to start with this. This is the approach, basically, to start from the segmentation, calculate the textural map using a filtering, and then to extract typical radiomics features from different patients. And these radiomics features mainly from all the different techniques that we already know. So co-occurrence matrices, run length matrices, gradients, so all the varieties that we find among texture literature and state of the art. And then we decided to open our initiative in a platform, an online platform, and we decided to make it open. Actually, the chest X-rays was the former part, but we decided to implement a CT classification. As you can see, this is the modules that are inside the platform. So we have the chest race classifier and the COVID-19 similarity score. I will not discuss deeply on that because Georg is speaking about CT here. So focusing on X-rays, we from 58 centers from different countries. No, we have from Spain, Italy, France, Netherlands, Belgium, UK, South Korea, so different countries, and we can find the platform here. We wanted to leave it open for mankind. We think that this is our commitment in this pandemic situation. And basically, whenever you upload a chest X-rays, is it possible for you to get the results of the classification? So just reviewing what we discussed yesterday, this is an example of bilateral findings of pneumonia and how we, in the end, focus in the normal probability score as an added tool for the radiologists, when they are reviewing hundreds and hundreds of chest X-rays on a daily basis, as well as this case, we are showing the main attention maps also of the network. And we have to understand that this is running completely automatically. So you don't need to do anything. The platform can be connected to the PACS. So basically it's crawling in the PACS for all the chest X-rays that are being generated. They go through the classifier and the results go back to the PACS again as a support for the report. This is not aimed to substitute the radiology report. This is another case where we can see the abnormal probability score, and we can see that the network has focused, either if it's a bilateral pneumonia, has focused only in one. This is mainly because of the bias of AI. We can see that the classifiers that we are showing are the mass ones, the consolidation, and therefore what we are plotting in these findings is the classifier that gives the highest weight, and this is the mass one. But probably the consolidation classifier is taking attention in this region as well. So this is something also related to the narrow that is AI nowadays, and in the end we are sensitive if we go to the abnormal score, but we are not so sensitive if we go class by class, that we have to use different classes to find relevant information. So this is an example of the population level analysis. So here we have different patients that we can see an example of how we visualize in the data miner, And a very basic way of showing this is we can have patients in rows and features in columns, and we can see that for every patient we can have the diagnosis and follow-up chest X-rays. And basically, we can use all this information to create, let me see if this works quickly. This is a video, but I will drive you to the precise point of the video. Okay, it's not working. But in any case, what I wanted to show you is that if we have the information from the features and the patients, it's relatively easy for us to apply non-supervised AI and to get automated disease phenotypes. So our hypothesis was, let's collect as many textural features as possible from all the chest X-rays and the patients, and then let's use non-supervised AI to automatically get COVID-19 phenotypes, because we are sure that we might find many surprises within all the clinical span of COVID-19, and we are starting to know few insights from the disease. This is the video right now. Sorry. Yeah. Let me drive you to the interesting part. Okay, so in any case, it's slow, but the idea is to have this automated classification. Okay. So just to finalize and to connect as well with Georg's presentation, what we did in CT. So we also, in that platform, we develop a CT classification. So we use a convolutional neural network We did segmentation of the lung parenchyma, and then we annotated the studies from the ground glass. So from one side, we can obtain the COVID-19 similarity score, which is highly relevant because we are not saying that this is a COVID-19 diagnosis, but we communicate that your CT is highly or likely similar to a COVID-19 ground glass regions and other affected areas, and this allows us to quantify the volume of ground glass per loaf or per thirds, no? And finally, we decided also to put all that knowledge in a European consortium. There have been many initiatives right now at a global level, and we are one of these. And basically what we want is to offer all the technology or as many parties as possible to solve from the imaging side this pandemic situation, in which we think that radiology has a responsibility in this pandemic moment, and we have to act fast and act proactively.
Yeah, thank you very much, Angel. As you already announced, Georg will now focus on the CT aspect of this analysis, of potential analysis.
Great. So thanks a lot. So yeah, in the next couple of minutes, I'd like to give you a bit of an insight in the multi-center trial that we've started here from Vienna. The idea is that we would like to, or we've started a trial or a study where we are collecting data, imaging data, and also clinical data, and also treatment data of respiratory infectious diseases, including, of course, COVID-19, but also other diseases. The idea is to do it in a multi-center study. We have currently centers from Austria, Germany, Spain, Italy, and the Netherlands involved here, who are contributing the data and who are performing research on the data. The data comprises CT, comorbidities, clinical parameters that might be relevant for the prediction of future severity and disease course for individuals, and also of the diagnosis and the differential diagnosis. The coordination is in Medical University Vienna, but the setup of the study is that many centers do contribute data, but the research is also happening in all of these centers. So it really should be an open data set where as many groups as possible can perform research on the data, because we believe the more groups are involved, the more diverse the ideas are that are coming out of that. The data collection is both retrospective and prospective, and that might also be a bit of a special feature or special aspect of studies these days. We need retrospective data in order to sample infectious diseases of the respiratory system, to have that as a control set, but also to learn more about the different diseases and what CT and AI can do there. And one part, and Angel already mentioned the initiative he and his group is involved in, I think it's critical to make this data computable so that we can merge data sets across different studies and eventually come up with a really rich data set that kind of represents the diversity of the disease, the population, and also the imaging parameters. And the second, I think, special characteristic of the study is that, of course, right now, it's not a good approach to do the study, wait for a year, and then develop algorithms or approaches based on the results of the study, but we need them right now as soon as possible. And so in the study that we are running, we are working together with ContextFlow, and they essentially built the software specifically for COVID, and this software is now running or is being installed in all of the study centers. This gives us an advantage, or the possibility to actually run this analysis from the start of the study to learn about the relevance of different roles of AI, and to also continuously kind of feed back what we learn, what we do research, what we understand better and better about the imaging science and the prediction models into the software that then can be used at the different sites. So right now, this software is running, it's running on a virtual machine in the centers, it's getting data from the CT, automatically performing the analysis and making that available to the radiologists as part of the study. In the phase one, it's about the detection and the quantification of the relevant patterns. You see that on the right-hand side, so ground glass opacities, consolidations, and others. We understand now the distribution of this case, of these patterns, the volume of these patterns, how they fill the lung and how they are related to the disease. And while this is already running and people are starting to understand better and better the link between these patterns and the severity of the disease, the outcome, the kind of treatment options, the phase 2 is building up to create the prediction models that then will go back into software in being available to all of the centers that are part of the study. And just to give you a brief glimpse, a sense of how this looks like. So on the left-hand side, you see the software that is running that allows you to look at your case, to compare it with other comparable cases, which I think is an important factor in order to kind of give you a sense of if this is really like a clear COVID case or if this is kind of a border case where you have to do more inspections. It provides you with a distribution of this pattern so that you can see that for your case, but also compare it to other cases. And one thing that was coming up because of a request of many of the users was just a very quick, fast track report that is generated while the data is routed through this virtual machine. That's just a downloadable, ready-to-use report that tells you about the quantitative characteristics of these patterns and the distribution in the data. And so the idea is to run this trial to learn more about these diseases, their CT kind of signatures, and the biomarkers that we are able to identify, and learn how to predict disease course, care need, to then use that for the treatment of individual patients. Thanks. I think I'll go back to Helmut.
Yeah, Georg, thank you very much. 2 quick questions. First of all, is this study still open to accept other partners who want to join? And secondly, do they have to use your software, or can they develop their own algorithms based on the data set accumulated by the consortium?
Yes. So no. So first of all, yes, the study is still open, and the answer to the second question, of course, everybody is free to develop their own software, to use their own software. I think that's also one of the key aspects of these kind of studies, that everybody should kind of develop, do research, and then be also able to roll out the results of this research and use them.
What I find very appealing is the combination of imaging data with clinical data, lab data, which adds another dimension to the whole results. And here, do you have a similar plan to also add clinical data to your analysis to improve the quality of your predictions, to improve the quality of your classification?
Yes, indeed. On the projects we submitted to the different ethics committee, to the different hospitals, we have a series of clinical data that complements all the information. So we define clinical endpoints from hospitalization times, ICU, yes, no, also the type of positive in the COVID on the PCR. So we collected also habits from the patients, from age and different data that we have in the project. And in the end, what we want to do is to use that data in combined models to see if it improves using that data alone versus clinical data plus imaging.
And there's a question coming in. Does CT give an advantage over chest radiographs when it comes to AI and the quality of your predictions? Okay.
Yes. I mean, what we have found is that the chest X-rays, at least from the AI perspective, are not so specific. And CT is giving us kind of different patterns of damage in the lung parenchyma that is mainly kind of COVID-19 more specific, and we can use it to make AI classifiers more not sensitive, because I think it's not a problem of sensitivity, but in 2 years' time, 3 years' time, where COVID-19 is, among all the respiratory diseases that we will face in radiology reading rooms, we will need tools with high specificity. And for that, I think CT definitely is the modality to go.
Thank you very much. But one thing is the specificity, one is the imaging data you have, and in many situations you just take chest radiographs. So I think it's not just a question about what is better, but also what is feasible. So I think both approaches are something we need. We don't need just CT, we need both approaches, and that's why I'm happy to have you here. I think with that, we have to close. There are some more questions on our list. However, we are running out of time. And with that, I would like to thank both of you, Georg and Angel, for your excellent presentations and your fruitful discussion. And I'm looking forward to welcome all of you in the next episode next week, which will also focus on another topic in COVID-19, the more clinical topics, and there are more clinical topics to come in the next few weeks. Thank you very much.
Thank you.